Well, hello everyone. Mikhail Golovnya. What I would like to discuss in the next series of videos is how to work with different cost functions. So we need to talk about the concept of cost function in general, why it's so important, and also what are the types of different cost functions and evaluation criteria are available out there for your disposal as analysts. The whole presentation will be partitioned into several parts. So we'll start with the general introduction into the concept of cost function. Then I will proceed with an at-length discussion of different cost functions available for regression. And then we will cover another exciting subject, which is the different cost functions available for classification, in particular binary classification. So let's get started and introduce things one at a time. Okay, so first, let me reiterate what a supervised learning problem is all about. It all starts assuming that you have a collection of np-dimensional feature vectors, and those are basically feature vectors x sub I. Okay. And there will be n of those vectors. So again, each subject is described by a set of characteristics, p-dimensional feature vectors, and there will be n of them. And then on top of it, we have a collection of observed responses, which is essentially y sub I goes to 1 to n. And the goal of a supervised learning problem is to construct a response surface, h of x, that somehow can be used to deduce what the responses are, how they relate to the available features, and also perhaps to make some predictions in the future. Now, one way to think about it is that the response surface here can be graphically presented as if we have some kind of model. This model accepts for any input feature vector xi, there is some kind of mathematical rule that generates output response surface h of xi. And the goal of supervised learning problem is to construct this response surface. Another way to think about it is that, suppose in this case we have a two-dimensional vector of features, so you have two different measurements that comprise vector x. So this x space can be represented as a hyperplane. And what we're trying to do, we're trying to construct some kind of response surface that looks like this. So for every available value of feature vector x, we can produce some kind of response surface value h of x. So that's the supervised learning problem in a nutshell. And the next important component that we need to introduce is the cost function. You see, the cost function describes how well the current response surface h of x fits the available data, assuming some kind of underlying data set. Now, the cost function j will be, in our case, essentially a function of predicted response and the actual observed response. One way to think about it, again, assuming that we have a unidimensional feature vector x, there is only one variable x that changes. And here you have response y. In this case, y assumes to be a continuous variable. And suppose that your observed data points look like this. Okay, so the machine learning algorithm will fit some kind of response surface that looks like this. So that's our h of x. And again, x is unidimensional in this case. And now the goal of the cost function is essentially to characterize the goodness of fit, how well this response surface h of x fits the observed set of y's. And that therefore we have basically those two components entering into the definition of the cost function here. Now, needless to say that because we call it cost function, usually the way it's constructed mathematically is such that the smaller values of the cost function will correspond to a better fit. In other words, if this particular curve here has some kind of overall cost equals J1, and then I also have an alternative fitting algorithm that goes like this, and this is another h of x function, and it has the corresponding cost associated with it as J2, then usually what happens is that if J2 in this case represents a model that has a poor fit compared to J1, then according to our definition, J2 will be greater than J1. Now, in regression, h of x is usually directly interpretable as predicted response. And that's something to keep in mind, because there are many different ways to construct this particular term that we call the response surface. And in some cases, it has a direct relationship to whatever we're trying to predict. In other cases, it may be a more convoluted relationship or additional interpretation, additional kind of specific steps needed in order to come up with the final interpretation. But in the case of regression, the situation is actually quite simple, because in this case, h of x is usually directly interpretable as the predicted response y. And therefore, we can essentially compress the overall goal of machine learning, as in this case, as the task that essentially boils down to constructing a response surface h of x such that j, or the currently selected cost function, is minimized. So that is, in a nutshell, the overall essence of the machine learning algorithm. So we want to fit some kind of response surface that returns continuous value for every potential feature vector x. And we're trying to fit that response surface such that the quality of that fit as returned by the cost function is maximized, which means that the cost function itself is minimized. Okay? Now, in the regression case, response surface is directly interpretable as what we're trying to predict. And this is going to be our first collection of cost functions. First, I introduce a so-called least squares deviation cost. So we have the formula presented here. And one way to define it is that the least squares deviation cost is essentially an average squared residual for the current fit. Now, one way to see it is, again, if I set some kind of data set here, and assuming that I already fit some kind of response surface that looks like this, so that's my h of x. And again, I have a univariate set of features, x, and a response y. So in this case, what happens is, suppose we take this observation over here, and so this observation corresponds to some particular feature x sub I value. Now, if you project this observation on the vertical axis, what you'll see is that this value here is essentially your y sub I, which is what you observe, whereas this value here is our prediction according to our response surface, and it enters here. And all that the least squares deviation cost is trying to do, it's trying to take the difference between those two, observed and predicted, and take the difference, square it, and then look at all of the available observations, average over observations, and that gives us the least squares deviation cost. Now, this value here underneath of that summation term is also known as a residual, or simply the difference between the observed and predicted values in the regression context. Now, why least squares deviation? It turns out that it has some nice mathematical and statistical properties. Now, mathematical properties is that you have a sum of squared deviations. Now, sum of squares is a nice function. It gives you nice derivatives. It usually results to nice quadratic forms, systems of linear equations, and it's just a nice mathematical form to deal with. On the other hand, statistical properties stem from the fact that the least squares deviation cost can be arrived at by introducing a maximum likelihood principle based on standard normality assumptions. Now, concretely, if you introduce the assumption that the conditional distribution of y given feature vector x, and this stands for probability density function, the conditional distribution of y given x is mathematically represented by the formula that includes e to negative, and here you get y minus h of x divided by some constant standard deviation, all squared. And again, for the simplicity of use, I skipped some of the constants here, some normalizing factors, etc. So this is a standard normality assumption. And this way, if you apply a likelihood principle here, so if you compute negative log likelihood, which is product I goes 1 through n, of this e to negative, this time y sub I minus h of x sub I divided by sigma squared. So if you take this and simplify, eventually you'll see that this is an equivalent of sum of I goes 1 to n of y sub I minus h of x sub I squared, which is directly gave us this least squares loss introduced over here. So the least squares loss is nice, and it does characterize the measure of fit. However, it has a problem with so-called outliers. In order to understand better what we mean by that, again, let me take another example here and suppose that there is a stray observation, say, over here. So for that specific value of x sub I, you have an observed response that kind of goes out of sync with the rest of the responses. So what happens in this case is that the residual, of course, is now represented by a very large value. And once that residuals enters into the least squares cost formula, it gets squared. And to make things worse, basically what happens is that when you have at least one or more of such outliers, eventually the entire least squares deviation cost will be dominated by model predictions on those outliers, and that may introduce all sorts of distortions. So least squares cost is nice. It has all of the good properties, but it has a problem with outliers. Now, one way to alleviate this problem is to focus our attention on this power factor here and simply remove it. If you remove it, of course, you need to handle the problem that the residual could be either positive or negative, and that can be rectified by simply taking the absolute value. And if you do that, you will arrive at the next type of regression cost known as least absolute deviation cost, or LAD. Again, it is defined in a very similar way. You have this average of the sum of absolute residuals. So these guys here, as you can see, these are now absolute residuals. And whenever you fit some kind of, again, some type of response surface, this time, instead of looking at the squares of the residuals, you simply accumulate absolute values associated with each individual observation here. Again, the cost, the least absolute deviation cost, can be naturally introduced as arising in the situation when we assume that the conditional distribution of y given x is double exponential. And what it means is that as far as the PDF goes, f of y conditional upon x is essentially represented by the term that includes this kind of relationship. So it's e to negative absolute value y minus h of x. And if you apply maximum likelihood principle through this assumption, then eventually it will lead you to this definition of a least absolute deviation cost. And it also explains why it has more robust features with respect to outliers. It's simply because it allows statistically much thicker tails, and it also doesn't take residuals as squares. It simply takes them as absolute deviation. So the only problem with the least absolute deviation cost is that it may pose additional computational challenges. And those have to do with the fact that the shape of this function, there are some specific points where the first derivatives are discontinuous, and you have all sorts of other difficulties related to convexity and all sorts of things related to when you try to minimize things or do some other mathematical manipulation with this absolute value over here. Okay, so this is the least absolute deviation cost. Our next cost is known as Huber-M, and this cost is introduced according to this, at the first glance, horrendously looking formula, but it also has a very nice underlying intuition. So again, suppose you have that this time that I plot a different graph where on the horizontal axis I'll introduce my residual that could be either positive or negative, and observe that the residuals are this term, and this term. So these are all of my r sub i's. And on the vertical axis, I'll introduce the jth component of cost function under this summation term. So basically here, if I take one of these terms, that becomes my j sub ith. And if we were to go back to quadratic laws and try to plot it on this graph, then what you would find is that, well, basically this is the 0 point. So when you have your residual is 0, the cost is, the contribution to the cost is 0. But as residual increases, when they have a quadratic cost, it goes up as a parabola here. Let me try to also plot it on the left-hand side. So that's the least squares loss. When you have LAD loss, it essentially goes as a 45-degree line. So that's the LAD loss. So it has this pointed tip, but otherwise it kind of nicely proceeds in a linear fashion. So what Huber-M cost is trying to achieve here, it essentially uses least squares loss on small residuals. So here it roughly approximates least squares loss. And then after reaching a certain threshold point that we'll call delta here, so this is going to be plus delta and this is going to be negative delta. Once the residual increases in absolute value past some kind of threshold, then it starts following LAD loss. And by doing this trick, by introducing this delta parameter over here, we managed to combine the best characteristics of the least squares loss and the LAD loss. So we kind of now have the machinery that allows you to capture both outliers and at the same time preserve some of the nice quadratic characteristics. And this is exactly what this formula here is trying to tell you. You look at the residual here. If the residual is less than delta in absolute value, then you take the square. Otherwise, If the residual gets too large, then you get the absolute difference. And the presence of the delta and 0.5 parameters here simply ensures that at these connection points, everything happens without any discontinuities or some kind of other difficult behaviors. Another way to think about the Huber-M cost is from the data point of view. So if you look at your data set, then usually you have a flat table where first you have a set of features. So those are your X features from 1 to P. And the observations go from 1 to N. Then you have a column of Y's. And the machine learning algorithm generates this hypothesis or response surface H of X. And knowing Y and H of X in the case of regression is directly interpretable as Y. So now you can calculate residual and take the absolute value. Okay. So once you have the residuals and you take the absolute values, you can sort residuals descendingly. So this is going to be the max absolute residual. This is going to be the min absolute residual. And now, what is usually done in practice, you take 10% of largest absolute residuals, so 10% here, and whatever value that cuts off that 10% of residuals is automatically taken as delta. So in other words, even though delta is introduced here as some kind of parameter, in practice, this delta is usually set automatically based on a specific percentile of absolute residuals. Okay, so what we see, we introduced 3 different loss functions, least squares, LAD, and Huber-M. And in the next slide, I'm going to show an example of the usage of such losses. Now, specifically, here is a screenshot coming from 3-net regression. 3-net stands for, it's a Salford implementation of stochastic gradient boosting based on the original Jerome Friedman's algorithm. Okay, so here's an example of a cost function in 3-net regression. And this is part of the 3-net engine configuration. And so what happens in this case is if you focus on this part of the display, you'll see that it lists the regression loss criterion. And in particular, you have a choice of least absolute deviation. You have another choice of least squares. And the third one, the default option, stands for Huber-M. Those are the 3 losses that were just introduced. In addition, you can also notice that there is this Huber-M fraction of errors squared located here. It's set to 0.9. It's directly connected to Huber-M. And what that 0.9 represents is that once at the end of any given specific iteration, once 3-net pauses in order to calculate Huber-M cost function, it generates all of those residuals, takes absolute values, sorts those residuals, and then takes 90% of smallest residuals, pushes them through least squares component, and the 10% of the largest residuals will go through LAD component. And of course, you can manipulate this parameter. If you make it larger, you'll make Huber-M behaving more like least squares loss. If you push it towards lower values, you will make the 3-net behaving more like LAD loss. Okay, that's all I wanted to say as far as understanding regression losses. So in particular, what we've realized is that in the regression domain, the interpretation of the response surface is typically directly interpreted as target itself. And then there is different ways to evaluate performance, and the typical ones that are used will be least squares, LAD, and Huber-M. And we also saw some examples of using it. So hopefully that kind of unveils the mystery of regression losses for you. In the next video, we will try to address a different case, and it has to do with the classification problem.